The uncertainty principle, a cornerstone of quantum mechanics, fundamentally alters our understanding of measurement. Formulated by Werner Heisenberg in 1927, it states that position and momentum cannot be known simultaneously with perfect accuracy. The more precisely we pinpoint one, the less certain we are of the other. Imagine tracking a tiny, fast-moving particle. Shining light on it to determine its position imparts momentum, changing its course. This inherent fuzziness is baked into the fabric of the universe. The uncertainty principle is about the subatomic realm, where particles behave like waves. This wave-particle duality is key to understanding the principle. Wave mechanics, pioneered by Erwin Schrödinger, provides a powerful framework for understanding the uncertainty principle. Particles are described by wave functions, mathematical expressions representing the probability of finding the particle at a given point in space and time. These wave functions evolve like ripples on a pond, spreading out and interfering with themselves. The uncertainty principle arises from the inherent trade-off between the position and momentum representations of these waves. Consider a wave confined to a small region, like a wave pulse traveling along a string. Its position is well defined, but its wavelength, and hence momentum, is uncertain because it's a mixture of different wavelengths. Conversely, a wave with a well-defined momentum, represented by a single long wave, has a highly uncertain position. It's spread out over a large region, making it difficult to pinpoint its exact location. A localized wave packet has a well-defined position, but a spread of wavelengths, representing an uncertain momentum. Matrix mechanics, developed by Werner Heisenberg, offers a different but equivalent perspective on the uncertainty principle. Instead of wave functions, it employs matrices, mathematical arrays, to represent physical quantities. In this framework, the uncertainty principle arises from the non-commutativity of certain pairs of matrices, such as those representing position and momentum. This means that the order in which we multiply these matrices matters, unlike ordinary numbers. When two matrices don't commute, it implies an intrinsic uncertainty in the simultaneous measurement of the corresponding physical quantities. This uncertainty is not due to any limitations in our measurement techniques, but is a fundamental property of the quantum world. Think of it as trying to measure the height and width of a rectangle simultaneously using a ruler that can only measure one dimension at a time. The order in which we measure affects the outcome, leading to an inherent uncertainty in our measurements. Planck's constant, denoted by h, plays a crucial role in quantifying the uncertainty principle. It's a fundamental constant of nature, setting the scale for quantum phenomena. Its value is incredibly small, highlighting the subtle nature of quantum effects. In the uncertainty principle, Planck's constant appears as a lower limit on the product of the uncertainties in position and momentum. This means that the product of these uncertainties can never be smaller than a certain value determined by Planck's constant. The uncertainty principle extends beyond position and momentum. Another significant manifestation involves energy and time. The energy-time uncertainty principle states that we cannot know both the energy of a system and the time it takes to measure that energy with arbitrary precision. This principle has profound implications for the behavior of unstable particles and the nature of virtual particles, which pop in and out of existence in violation of classical energy conservation, but are allowed within the limits set by the uncertainty principle. Imagine trying to determine the energy of a short-lived particle. The very act of measuring its energy over a short time interval introduces an uncertainty in the time at which the particle had that energy, and vice versa. This principle is crucial in understanding radioactive decay, where the lifetime of an unstable nucleus is inversely proportional to the uncertainty in its energy. It also plays a role in quantum tunneling, where particles can borrow energy for a short time to overcome potential barriers. The uncertainty principle emerged from the early 20th century, during the birth of quantum mechanics. Werner Heisenberg formulated the principle in 1927, based on matrix mechanics and wave-particle duality. Heisenberg's principle challenged classical physics and sparked intense debate. Despite initial resistance, it has withstood the test of time and countless experiments. It remains a cornerstone of quantum mechanics, shaping our views on reality and knowledge. The uncertainty principle's implications extend far beyond the realm of physics. sparking debates in philosophy, metaphysics, and even theology. It challenges the deterministic worldview, suggesting that chance and probability are woven into the fabric of reality. Some philosophers argue that the uncertainty principle undermines the concept of objective reality, suggesting that the observer plays a fundamental role in shaping the observed. Others see it as evidence for a fundamentally probabilistic universe where determinism is replaced by a tapestry of possibilities. The uncertainty principle also raises questions about free will and determinism. If the universe is inherently uncertain at the quantum level, does it leave room for free will, or are our actions predetermined by quantum fluctuations amplified to the macroscopic world?